So I'm afraid Josh spoiled half of my presentation. You will see why. Just a few words about me. 6 months ago or so, IBM management asked me and a few others to think about what could be an IBM machine learning offering. And why me? Because I have a PhD in machine learning, so I should be expert. Unfortunately, my PhD was from last millennium, so it's no longer relevant. So I've looked at what has changed in 25 years in machine learning. So 25 years ago, that was a machine learning workflow. You had some data. Your goal was to find a machine learning algorithm and publish it. That's all you could do. Quite a few algorithms were devised at that time, like stochastic gradient descent, convoluted networks, to name a few hot topics of today. But this was just academia. So what is machine learning now? If you read newspapers, blogs, this is what you see. So all you need is a machine learning algorithm. That's all. Some people are a bit smarter, and they say, well, you need few more ingredients. You need a data scientist, a unicorn. And the data scientist with the algorithm will produce the model. And then you have the outcome. It's partly true. And for machine learning algorithm, today we have a lot of possibilities. I name a few. Issue when you create lists like this is that you immediately antagonize everybody who's not on the list. So I'm sorry for that. Let's say I've put the tools I've used recently. It's not an IBM selection at all. It's my usual toolkit, let's say. Is that as simple as that? Is it all you need to make money? That there is a danger in this simple view that we know that a chain is only as strong as the weakest element. So this leads people to think that you need to hire the best data scientists in the world. And this is what drives data science salaries high, which is good for us, but I'm afraid this is not enough. So let's be a bit more realistic. And when we see this at IBM, we say, well, we do have some algorithms. I will mention stuff, but open source community is so good at spitting out new, very useful libraries every year. We had great presentation all over the day. Some of them are not listed here. We won't compete on algorithms. But what we will try to do is, if you have your favorite algorithm or favorite set of algorithms, we will try to help you bridge from data to the business outcome. That's our angle at machine learning. So if we look a bit more into detail, it's a bit more complex. From a model, you don't get business outcome immediately. You need to make predictions. This may seem obvious, but how many people only build models and never care about how they are used in production systems? So you should care. And this means you need to move your model from where you build it to where it has to be used. This we call deployment, and it's a bit complex. What I've observed in the past, the problem is that the tools used to build models and the tools used in operational systems are very different. Tools used to build models, well, I've listed several open source, but you don't develop necessarily a transactional system or a scoring system on a gateway in an IoT setting using R or Python or any of the machine learning toolkits. You will use maybe C++ directly, you will use Java, I don't know. You will use a tool for the task. And deployment usually means recoding in practice, which is not very good. So, in fact, we are facing several challenges when we believe we solve machine learning. Here I list, I didn't sleep that much with a jet lag, but here are a few challenges that we're facing. I will discuss the scalable and deployment first. When I was preparing this a few months ago for internal use, I just picked some tweets. They are very representative of reality. You have a data scientist that comes say, okay, I have this great R script that does everything with shiny front end. Can you just put it and add billing to it and logging? Or I have those Python scripts that are great. Can you deploy them for me? And this is a reality developers are facing. Data scientists come with models that are not ready for production. It's not their fault. So what we need to do is to look at the big picture. Typically, a machine learner will take example, prepare data, run algorithm, create a model. That's a development environment. The machine learning, the operation team will need to take the model in a system, in an operational system, to make predictions. The problem is, how do you move your model from the top to the bottom? As I said, open source is great at helping the top row. We have lots of algorithms. But when it comes to put models into production, there is less effort. And what we really need is for each machine learning toolkit, we need a way to serialize models so that they can be moved. And then we need a scoring engine or inference engine or serving engine, call it as you want, to run those models on new data. Some open source include a serving engine. Most don't. And for instance, we're big on Spark at IBM. We are developing serialization for Spark ML models and a serving engine for Spark ML models. I wish all open source communities were spending as much time as easing the bottom row of this slide as they are easing the top row. So let's go back to the machine learning workflow. Well, let me just say, for Spark ML, what we did is simple. We are serializing all models to JSON, and then we create an interpreter of this JSON to score efficiently. We don't run Spark in the scoring engine. It's not meant for that. It would not be very efficient. So, sorry for the animation. Assuming we know how to deploy, how do you select which model you want to use? How do you select which algorithm you want to use? This is extremely time-consuming. The right way to do it is to design an experimental setting before you actually create models. Then you run it, and you take the outputs. This is very time-consuming. So we have been working on a system called Cognitive Assistant for the data scientists. I think there is a paper at every major conference about this system. This is not HPO, so it's not Bayes optimization for selecting parameters. This is about building machine learning pipelines. So it's about combining feature engineering, data preparation steps, and actual machine learning steps. And this across platforms. So today, we are able to generate pipelines that combine our Spark, scikit-learn, and our proprietary SPSS technology. And this does a search, the search space is so big that there is no way we can use a complete search. So we're using, it's not base optimization either, but basically we're starting, it's a kind of beam search. We're starting with a lot of pipeline candidates, and each of them is assigned a small subset of the data. Then we evaluate quality when they complete, and the most promising one are given more data. And we extrapolate, then after a few iterations, we have a curve of how the quality of a given pipeline increase with the size of training data it is given. We extrapolate, and we use this to rank to which pipeline do we send more data next. And this is quite efficient. Our experiments with IBM data scientists internally, that typically in a day, the system gives the same quality of pipelines as a data scientist in 2 weeks. I'm not saying that if it runs 2 days, it will do 1 month's worth of data scientists. It's not linear. There is a point where the human-driven work outperform this, but this is a great tool to start with. So we plan to make this accessible via our offering soon. Another tool which is open source that we have called SystemML. It's a compiler for machine learning algorithms. Its value is that, well, you have a high-level language, but it's not the only one. A lot of deep learning toolkits have high-level APIs. The value of SystemML is to be able to generate code that targets the runtime we want to run on. So it can go from single machine to very large Spark clusters. It's open source, so you can try it. So back to our machine learning workflow. With all what I'm promising, you could say, okay, we can automate data preparation, training, deployment. We're almost done. Not so fast. There is an assumption that the better your predictions, so the better your prediction on your validation data, the better the outcome. So let me give you an example where it's not really clear. So a telco company was building a churn model, so predicting which customers are likely to not renew their subscription. So their data science work used past to learn, and at some point they believe they have a good quality model, so they decide to just run it on the current customer base and send the names of those customers with a high predicted risk to the customer relationship department. And so this department is given a list of customers, and they decide to call each of them to try to get them renew. What do you guess is happening? Often this happens. A rep calls the customer saying, hello, Mrs. Smith, you're about to renew your subscription. Oh, it's good you called me. I wanted to cancel. Thank you. Let's do it now. So, and the more accurate, the worse it is for the business. And it was said, I think it was Airbnb, or the quality of predictions, whatever metric you use, F1 score, RMSE, whatever, you're not measuring the business impact. Really what matters is what is it you're learning for. And you should measure what you want to improve. That's the basic of machine learning. You should measure, you should have a business metric you monitor, and your predictions are meant to help increase or maintain this metric. So you need to monitor. Another reason why you want to monitor is when the quality of your prediction is linked to the quality of the business outcome, like fraud detection for credit card payment, you want to monitor how your prediction go compared to reality. At some point, usually what happens is you have good accuracy, and at some point, criminals find a way to use stolen credit card info in a way that your model does not detect. And all of a sudden, your prediction accuracy drops. If you're not monitoring, there is no way you can notice this. So you need to monitor. And when accuracy drops, or when your business metric drops when you believe it should increase, then you have to go back at the start and redo your work. The other bottleneck that is even worse and unnoticed is you need examples. So I know unsupervised learning exists, we can have anomaly detection, what have you, but when you know what you want to learn, it's hard. When you don't know what you want to learn, it's harder. So in general, you want to start from examples. And producing examples, labeling data is time-consuming or prone. I think the image recognition community is spoiled by the existence of ImageNet. It's too easy. This has been done. But here is an example. I was asked to help for a sales of IBM Watson. It's a machine learning system. And the customer was complaining that it was consuming to create examples, and they were asking if Watson could help create the examples. So they have it completely wrong. I mean, they want the learning system to create the example it will learn from. This is the level of misunderstanding of business people. So there is a way to kill two birds with one stone, is to use the feedback you get from how your predictions compare to actuals, just to generate more examples. And if you think of recommender system, that's what they do. And a lot of successful machine learning applications are just using the gap between predictions and reality as a source of examples. So examples are acquired automatically. And I believe this is very, very important. So the goal of our machine learning offering is to help people, implement this loop. And we will tell people, bring your own machine learning algorithm, and we will help you for the rest. So I will move to another topic in the few minutes I have. So I said I have a PhD in machine learning. I'm now working on machine learning, and in between, for 2 decades, I went working on mathematical optimization on a product called Cplex. You may know about it. And when I came back to machine learning a couple of years ago, good news was it's all about optimization. Oh, yes, I must have a Watson slide, right? I'm from IBM. So that's my Watson slide. Cognitive computing and Watson is based on machine learning. It's machine learning plus natural language processing and a few other stuff. But machine learning is at the core, and everything I've discussed so far is now in beta under the name of IBM Watson Machine Learning. We're welcoming beta testers. You can go to the booth if you want to join. So, mathematical optimization. Most machine learning algorithms are optimizing something. And we had talked earlier today speaking about this. Basically, you're given a family of models. And you want to find the model that minimizes a loss function, the prediction error, as well as some model simplicity. Otherwise, you may overfit. And the algorithm used to solve these optimization problems are what we call local method. You basically have one parameter setting, then you iterate, you try to find a better one, and you iterate until you're kind of stuck in a local minima. And the methods are like stochastic gradient descent, conjugate gradient, LBFGS, follow the regular leader, Newton method. But they are all based on you have one point and you move it along the cost surface until you find a minimum. The great news is these algorithms scale well. You can scale to billions of examples. You can parallelize efficiently, as was explained earlier today. Drawback, it's a local method, so you can be stuck in a local minimum. And more important, they work on unconstrained minimization. So it's hard to have additional constraints on what you try to minimize. To the contrary, mathematical optimization, like Cplex and its competition, these are global optimum solvers. So they will find, if they are given enough resource, the true optimum. They can deal with constraints. The drawback is they don't scale as well. They are hard to parallelize. They can be, but they won't scale to terabyte data. But when when data is within range, it's interesting. So let me give you a couple of examples. So we've been implementing classical algorithms. We're going to look at tree ensembles and neural networks next. But let me give one example, lasso. So lasso, it's linear regression with L1 norm. So basically, we're minimizing the square of errors plus the sum of absolute values of coefficients. The interesting thing is this sum of absolute value, L1 norm, leads to sparse models, so models with a small number of non-zero coefficients. If you want to run a mathematical optimization solver, you need to change a bit because absolute value, it's not differentiable, it's not very friendly. Same for gradient descent, by the way. So we will just move it to constraints. So we just create additional variables that are greater, that represent the absolute value. And then we have a problem we can solve, which is made of linear and quadratic terms. Then we have very simple constraints, but we can add additional constraints. And for instance, here is an example for image reconstruction. So it's taken from scikit-learn. You're given a black and white image, so pixels have 0 and values, and you're given projections of it, so you have lost a lot of information, and the goal is to reconstruct. The middle image is what lasso produces. But if you think of it, when you reconstruct the image, you know that the pixels are 0 or 1. So we can just add as a constraint, when we solve it with Cplex, that all pixel values must be between 0 and 1. So here, in addition to the constraints on the coefficients, we are adding constraints on the weights, on the results, saying that all predictions must be between 0 and 1. When we do this, we get the image on the right. The reconstruction is way, way better. And another way to see it, we look at the distribution of pixel values. So the blue curve at the bottom is the original image. So you have zeros and then ones. The green curve are the pixels predicted by lasso. You see that values can be arbitrarily high. And when you add as a constraint that the values cannot be greater than 1, then you have a distribution that is way closer to the original. Another example, matrix factorization used in recommender system. So you basically build 2 latent vectors, one for each user and one for each product, movies, and you say that you want that the rating of a film by a user is a product of the profile of the user times the profile of the film. You want to minimize the square of the error compared to the rating, and then you have some regularization. This works well, but same story. You know that any rating is between 1 and 5, so you can add it as a constraint on some of the unobserved ratings. And when we do it, so here you see the quality, so the RMSE as the algorithm iterates. The red curve is alternatively square, which is a classical algorithm for it. And the other curves are what you obtain when you constrain further a proportion of unobserved ratings to be between 1 and 5, not outside of it. And we see that convergence is way faster and quality is way better. So these are very preliminary, but I just I'm surprised that the machine learning community is completely ignoring mathematical optimization. And this I can't understand. When I say completely, there are a few exceptions. One is also using the L0 norm. So instead of using lasso, you just want to minimize the number of non-zero coefficients. That's another use for us. So I will stop here because I'm in the red since a few seconds. So if you want to try our machine learning beta, here you have a link. SystemML is an Apache open source. CADS, I should have put the URL, sorry. There is a paper in each major machine learning conference. And for the Cplex Learn effort, I just put people because we have not published yet. I will stop here.